All right, so today is Thursday, March 11th. It is my dad's birthday. I sang to him this morning on my way to work in a voicemail. But we are factoring higher degree polynomials today. So we have dealt with a lot of quadratics with our product sum charts. And now we're going to look at factoring any polynomial. Not everything can be factored, but if I ask you to factor, it will be able to be factored. So we're going to look at factoring some higher degree polynomials, maybe to the third power or the fourth power or the fifth power or the sixth power or the eighth power. What? So kind of crazy stuff. So big tip, you always want to look for a greatest common factor first. If I don't look for a greatest common factor first, I might get frustrated. One of my patterns may not work. When I make a product sum chart, my numbers are just going to be large. So look for a greatest common factor first and then move forward. So the main types of polynomials that we'll be factoring are binomials, which have two terms. Wait for it to focus. There we go. Trinomials, which have three terms, and then a four-term polynomial. Now, it is possible to factor a polynomial with 5 terms or 6 terms, but we will not. So we'll be dealing with 2 terms, 3 terms, and 4 terms. So when dealing with binomials, we're going to look for a special pattern. And there are 3 formulas that we're going to go over in dealing with patterns. One of them, the difference of squares, you should be familiar with. So the difference of squares, if I have 2 terms that are both perfect squares and I'm subtracting them, hence the difference, it will always factor into the square root of those terms in a factor, one with the plus, one with the minus. So an example of this would be if I had x squared minus 25. Perfect square x squared, perfect square 25 being subtracted. This will always factor into the square root of the 2 terms, one with the plus, one with the minus. So let me show you how this works. If I do x times x, I'll get x squared. X times negative 5 will be a negative 5x. 5 times the x will be a positive 5x, and negative 5 times negative 5 will be a negative 25. These middle terms will cancel out because if I think about the difference of squares in a trinomial format, I'd have x squared plus 0x minus 25. So in a product sum chart, my product is 1 times negative 25, and my sum is 0 because I need them to cancel out. So a positive 5 and a negative 5 are going to cancel out. So anytime you have 2 terms and they are both perfect squares being subtracted, I can always follow this pattern. Right? This only works for difference. I cannot add together 2 perfect squares. In order to get the positive and the negative here, it cancels out, but I have to have a negative 25 because that's a positive 5 times a negative 5. If these happen to be the same values, identical, just add another paper here. So if I needed to, or I wanted to get, let's say, x squared plus 25, it would be great if I could do x plus 5 times x plus 5. But if I multiply these out, starting with my x, we'll have x squared plus 5x. And then with my 5x, 5 times x, and then 5x times the 5 would be 25. I'm going to end up with a positive 10 in the middle. So in order to cancel out that middle term, I have to have a positive and a negative 5, but then I can't get a positive 25. So this, the sum of squares, does not factor. So you have to subtract the perfect squares. All right, so difference of cubes and sum of cubes is something that's brand new. They have formulas, they each have their own formula, but the formulas are very similar. So these are new, and these deal with cubed values, so raised to the 3rd power. So I'm going to write down the formulas, I'm going to show you how they work. You will need to commit these formulas to memory by the unit test, which will be the week of the 22nd, somewhere in there. So difference being subtracted, perfect cube, perfect cube. So here is my formula, a minus b times a squared plus ab plus b squared. I'm going to prove to you why this works. There's a not very easy way to derive it, but this works. And then my sum of cubes is very similar in format. A cubed plus b cubed will factor into a plus b times a squared minus ab plus b squared. So please write these down on a piece of notebook paper. You'll need to commit them to memory. I would recommend every time you deal with the sum or difference of cube problem, you write down the formula, so it's going to help you memorize it. But something to notice, these are just opposites, and they look like what the original did without the cubed. So if I can cube root the two terms, I just put them in this cute little one. And then I have this longer one, and this longer one is almost identical except for the middle term. One I add, one I subtract. So if I'm subtracting in the little, because I'm subtracting in the original, then I add in the middle for the big. If I'm adding in the little, because I added in the original, then I subtract in the middle for the big. And good news, these two will never factor any further. So you always want to factor as far as you can possibly go. So I would like to prove to you, I do teach geometry, and I do appreciate a good proof, why these factor into these. And I'm going to prove that just by multiplying them together. So I'm going to start with my difference of cubes. So if I take my factored format, a minus b times a squared plus ab plus b squared, and I multiply them together, I should get this a cubed minus b cubed. So let's just check it out. I'm going to start by distributing my a times all three of these terms. So a times a squared is a to the third. A times ab is a squared b, and a times b squared is ab squared. All right, now I'm going to distribute my negative b. I'm going to keep my terms in alphabetical order. So b times the a squared, I'm just going to write the a part first. And I'm going to write it underneath this here so that my terms line up. So negative b times a squared, that's going to be a negative a squared b. Those will cancel out. Then I have a negative b times ab, so that's going to be a negative ab squared. Those terms will cancel out. And then I have a negative b times a b squared, which would be a negative b to the third, which won't cancel out. But when I combine like terms, I'm left with a cubed minus b cubed. Isn't that cute? So I'm going to do the same work for the sum of cubes and show that I do get a cubed plus b cubed when I multiply those together. So let me change colors. Go with green. Got these cool pens. They're paper mates, but they're super fine, and they got cool colors. Every teacher loves colored pens. Maybe not every teacher, but most. All right, so sum of cubes. So I'm going to multiply these two factored together to get the original. So a plus b times a squared minus ab plus b squared. So I'm going to start with my a and distribute here. So a times a squared is a cubed. A times negative ab is a negative a squared b. A times b squared is a positive ab squared. Then I'm going to take my positive b and distribute, again in alphabetical order. So b times a squared will be a squared b, and it's positive. B times negative ab will be a negative ab squared. And b times b squared will be b cubed. I'm going to combine like terms, add these together. I see that I have some zeroed terms that cancel out. Well, that's super nifty because I'm left with a cubed plus b cubed. All right, so you will need to memorize these two formulas. You won't need to prove them again, but know that they do work. And when you factor, this is a quadratic and this is a quadratic. They won't go any further. And I'll show you an example of why they won't go any further when we do them together. Okay, so if I have three terms for a trinomial, whether it's a quartic or quadratic or quartic, or any even degree really, This works for any even degree. We're going to use the product sum chart. So we're pretty familiar with the product sum chart, I hope, but just to refresh, 3 terms, I'm going to have ax squared plus bx plus c, or I could have ax to the 4th plus bx squared plus c, where I have a quartic, and then this is a quadratic, and this is a constant. But I always do, for my product, a times c to get the product number, and then b for the sum. When in doubt, you can list these out, and it should work. All right, and then a 4th term, four-term polynomial. I like to group it. You're gonna group it. Right, so we'll do an example of grouping here, and then I'll have you chain it out with me later. All right, so I've got 5 examples of factoring. And all right, so problem number 1. First thing I'm going to do, look for a GCF. So if my GCF is 1, that's boring. Nothing to take out really with the 1. So 4x squared minus 1, I don't have a greatest common factor other than 1. So this is a binomial. It has 2 terms. It is a difference because they are being subtracted. And then 1 is a perfect square and a perfect cube, but 4x squared is a perfect square. So it's a difference of squares. So here's my thought process that I'm writing down. And then I'm going to write down my formula. If I have a squared minus b squared, that will factor into a plus b times a minus b. So what I really need to know is, what do I square to get 4x squared? What do I square to get 1? And then I square root them. So my a term is what I square to get 4x squared. Don't forget about this coefficient. So in order to get the coefficient of 4, I need to get 2 squared. And then to get x squared, well, I just do x and squared. So this is my a term. And then my b term is what I squared to get 1. It's just 1. All right, so this factors into 2x plus 1 times 2x minus 1. And I'm done. That's all I have to do. Something to note, these are both linear factors. Linear meaning that I have the exponent of 1 for my x value. When you have linear factors, you know you're done. If you don't have linear factors, you might be able to factor more. And I have an example of that too. All right, looking at number 2, I want to factor this bad boy. So looking for a greatest common factor, there is not one between 27 x cubed and 1 other than 1. So it is a binomial. It is a sum because I'm adding, and these are both perfect cubes. So if you have a sum, it has to be cubes in order to factor, but 27 is something raised to the 3rd power. Let's go and figure out what that is now. So 1 to the 3rd power, 1 times 1 times 1 is 1. So that's my b term here. I need to raise something to the 3rd power to get 27x cubed. Well, I know it's going to have x, but in order to get 27, I need 3 times 3 times 3. I'm hoping that you will get good at finding perfect cubes in this process. But here's my formula for a sum of cubes. So a cubed plus b cubed. The more you write this, the more likely you are to have it memorized. So I highly recommend writing this down every time you use it. That's really the only way that I have it memorized. When I was in school, we didn't do sum or difference of cubes, so I never memorized these. I memorize these as a teacher because I write it down a lot. Okay, so there's a small one and a big one. The small one mirrors the original without the cubes. So that's the 3x and the 1 without the cubes. So my small one is 3x plus 1. If my original is a plus, then the small one is a plus. Now my big one, this needs to be a, which is 3x squared. Please don't forget to square the 3. It's the #1 mistake. So it will be 9x squared. So the entire a term gets squared, which is 3x, because 3 times 3 times 3 is 27. So I need 2 of those 3's, 3 times 3. Because in order to get this 27x cubed, I'm going to multiply 3x times 9x squared. That's going to give me my term here. Okay, moving on. My negative AB, I multiply these together, but I use the opposite sign for the middle. The big one always uses the opposite sign. So I'm going to do minus 3x. and then plus b squared. B is 1, so this is 1 squared, which is 1. The first and the last and the large one will always be positive because I'm squaring them. The one in the middle could be different. So I told you that this quadratic that is left over after using the sum of cubes will not factor, but I want to show you how this example won't factor. It's always good to try it. So I have a trinomial. Anytime you have a trinomial, you can make the product sum chart. So my product is going to be 9 times 1, which is 9. And then my sum needs to be -3. Well, the ways to multiply together to get 9 are 1 times 9 and 3 times 3. When I add 1 and 9, I get 10. If I were to make that a -1 and a -9, I'd still get a +9 product, but I get a -10 sum. Still not -3. 3 times 3 is 9. 3 plus 3 is 6. And if I use the negatives, -3 times -3 will give me -9, but -3 and -3 add together is -6, still not -3. This will never factor. This will actually give me 2 imaginary solutions. So whenever I have the sum of cubes, I've got a cute little 1 that'll give me a linear factor. This quadratic factor will not go any further. It gives me imaginary solutions. If you recall, if I have a quadratic, just a little side note. So quadratics that have imaginary solutions do not touch the x-axis. Right? So if I have a quadratic that looks something like this, it only has imaginary solutions. If I graph this on my handy dandy graphing calculator, I will see that it does not touch the x-axis. So here is my quadratic here, 9x squared minus 3x plus 1. If I hit graph, I will see when it gets there. There we go. It does not touch the x-axis. So imaginary solutions. So graphing can help you with factoring. Like, does this factor any further? If it touches the x-axis, then the answer is probably yes. If it doesn't touch the x-axis, then it definitely won't factor. All right, so that's 2. Looking at problem number 3 here. I'm going to look for a greatest common factor. So 216 is a pretty large number. 125 is 2, but my x is cubed, so it's a binomial. It's a difference. Will anything go into 216 and 125? Well, let's think about 125. I can raise 5 to the 3rd power to get 125, meaning that I have a nice cube value for the 5. And 5 will not go to 216, because if it went into 216, then the last digit would be a 5 or 0. So no greatest common factor here. So 216 needs to be a perfect cube. I won't give you a problem that won't factor. What do I raise the 3rd power to get 216? I raise 6 to the 3rd power to get 216. You should get better with memorizing your cubes. So let me write down my formula. A cubed minus b cubed. Now I'll factor into a minus b times a squared plus ab plus b squared. The small one looks almost identical without the cubes. The middle one has a term that's the opposite, but everything else is the same format. So this is my a value, 6x, and my b value is 5. So my small factor will be 6x minus 5. My large factor, I need to take my 6x and square it. So that will be 36x. Then a plus. So this middle term is going to be 6x times 5, which will be 30x. And then this last term is 5 squared, which is 25. Always positive. Now, this does not factor. You can just take my word for it. I can also look at the graphing calculator. Oh no, I forgot my squared. Good catch there, 36x squared. So 36x squared plus 30x plus 25. So here I have it typed in. And then I'm going to graph it and make sure that this graph does not touch the x-axis. Not sure I'm going to see it because it has a y-intercept of 25. That's my, nope, not going to see it. So let me just change my window. And I need to go higher. So let's go up to 100 for my y value. Oh, there it is. But does not touch the x-axis. So this does not factor. You don't need to waste your time in trying to factor this. Okie dokie. Looking at a couple more problems. All right, so looking at number 4, I have a polynomial with 4 terms. I like to group it. We're gonna group it. Okay, so first let's look for a greatest common factor. So there's factors in common, but I need all 4. So 20x cubed, 12x squared, 5x, and 3. There's not a number or a variable that goes into all of them. So I'm going to go ahead and group it. I'm going to put the first 2 together in a group and the last 2 together in a group. Now, it looks like I'm multiplying here when I put my groups in because that negative needs to go with the 5x. So just stick a little plus in there. It's not super necessary. It's not like wrong if you don't have the plus in there, but I don't want anyone to think that I'm multiplying. So 2 different factors or 2 different sets of groups that I'm adding in between. Now I'm going to look for the GCF of each group. So 20x cubed, 12x squared. I can take out a 4x squared and then be left with 5x plus 3. All right. Hey, those are pretty similar. The leftovers from the groups must match. If they don't, you have made a mistake. Or it doesn't factor, but I'm going to ask you to factor what can be factored. So negative 5x and negative 3, I can take out a negative 1 and then be left with 5x plus 3. So when I write these as factors, because right now I just have a coefficient and a coefficient, so I'm going to put these 2 coefficients together as a factor. So 4x squared minus 1. And they're going to be multiplied by the 5x plus 3. But since I combine these, I only need to write my 5x plus 3 once. If this makes you uncomfortable, why are there not 2 5x minus 3s? Please send me a message so I can explain to you why. But the coefficients go together, then I have 1 5x minus 3. Because I have 4x squared times 5x minus 3. And then I have a negative 1 times the 5x plus 3, which is what I have here. So looks like I'm done, but I'm not. So if you were to do this problem, I would ask you the question, can you factor any further? And the answer for this is yes. So we are looking for our goal, which we don't always obtain our goal, is to get linear factors. So when I dealt with number 3, I did not have all linear factors. So this is a linear factor, degree 1, but it was a quadratic factor for this one. But this will never factor more because it came from the difference of cubes. I have a linear factor. So this one is a linear factor. And I have a quadratic factor. This quadratic factor can factor further. So I need you to factor as far as you can to see if you can get linear factors. You can't always get them, but sometimes you can. Hopefully this looks familiar. Hopefully this looks familiar. We did it in number 1. It's a difference of squares with a 4x squared minus 1. So I kind of did that on purpose. So this will factor into 2x plus 1 times 2x minus 1, and then that will be multiplied by 5x plus 3. This is my final answer. So always look to see if you can get linear factors, linear factor, linear factor, linear factor. I know that I'm done. Not a linear factor, maybe I'm not done. Maybe I can go further, so always check. All right, got one more problem here. This is to the 4th power. So this has 3 terms. So this is a nice trinomial. So I'm going to make my product sum chart. Something to notice, it is to the 4th power. If I have 3 terms, I can use a product sum chart as long as I have an even leading exponent, and then the middle term has the exponent half of that. So when I'm done factoring, I want x squared and x squared up front, because x squared times x squared will give you this x to the 4th, and I'll show you how this works. So for this problem, still my a times c, so I have 1 times negative 13, which is negative 13, and then my sum is my b, negative 12. Well, there's only one way I can multiply to get 13, and it's 1 times 13. And if I want a negative 12, I'm going to make my 13 negative. Don't forget about that leading coefficient. It's 1, so it doesn't really do much here. But if I had a leading coefficient that was not 1, then I would need to deal with it in order to simplify my factor values here. So I have 1x squared plus 1 times 1x squared minus 13. Starting with x to the 4th, your first term in your 2 factors will always be half of what your degree is. So we don't really need the 1s with the x squareds. These are not linear factors. So I would ask the question, can you factor further? So let's investigate. 2 terms. It is a sum, but they are not cubes. It is a sum of squares. This does not factor any further. This does not factor any further. Looking at this one, it is a difference. X squared is a perfect square, but 13 is not a perfect square. So not a perfect square, so I really can't factor any further for this. So this is my answer. So you need to make sure that you can determine if I can factor further and go from there. All right, so your homework for today, this is posted in Canvas, is this factoring polynomials homework page. 2 terms, 3 terms, 3 terms, 3 terms, 2 terms, 2 terms, 4 terms, 3 terms with x to the 8th power. What? X to the 8th power. So this has 4 terms. So you're going to use all of the steps that we used in our examples to see how to factor. So binomials, look for these. Trinomial, product sum. 4 term, you're going to group it. Always look for a GCF first. I will be in school on Friday, the 12th. It is a teacher work day, but if you have questions on this homework, feel free to send me a remind message and I will get back to you. Have a great day.